All right, let's rock with practice problem number 5 associated with sample problem C here in chapter 4. Now we got to start reaching into our memory packs and using some old friends here. Okay, so let's get going. A 2.0 kilogram otter. Okay, so we have a mass. Starts from rest. Right, so that initial velocity is 0. At the top of a muddy incline, 85 centimeters long. So 85 centimeters long, that sounds like a delta x, right, a displacement, and slides down to the bottom in 0.5 seconds. That sounds like time. So just looking at what we've identified here so far, I'm hoping you're at least thinking about this old kinematic equation here. Okay, at least be thinking about it for now. What net force acts on the otter along the incline? Net force. So here in chapter 4, specifically sample problem C, we're looking at problems that use the mathematical expression of Newton's second law, F equals ma. And you can see from this last part of this question, what net force, right? Solve for F, right? Solve for F. Acts on the otter in the incline. Well, the otter has a mass of 2.0 kilograms. So we're being asked to solve for force here, like what net force. We've been given the mass, but we don't have the acceleration. But what we do have is a bunch of other information that we can use to calculate acceleration using our old kinematic equation buddies. Now, once we solve for acceleration here, then we can plug that into acceleration in Newton's second law. So let's get started. First thing I want to point out, if initial velocity is 0, it means that this value is 0. And so that actually, no matter what the value for time is, that actually goes away. So we actually have 1/2 acceleration multiplied by time squared. But I don't need delta x. I've been given delta x. I need to solve for acceleration. So I'm going to rearrange this. Okay. So I'm going to get rid of time squared by dividing both sides. I'm going to get rid of multiplying by half by multiplying by 2. Right, same thing as dividing by half. Okay, let's clean this up. So that canceled. Clean it up. So I have acceleration, as I've rearranged it, equal to 2 times the displacement divided by that change in time. You guys want me writing the deltas in here? You guys want me to have deltas? You like deltas? They make everything look more official, but they just take time to write. And I always make them look janky, and it distracts me because I'm bad at writing triangles. But here's my rearranged expression that solves for acceleration. And again, I have delta x from the question, and I have delta t from the question. And so I can solve for this. So I have 2 multiplied by 0.85 meters. Okay. Now this was given to me in centimeters. Okay, centimeters, and you do not want to put centimeters in the calculation. And I'll show you here in a second. Let me finish writing this out. And then what do we have? 0.50 seconds, and that is squared. Okay, so realize what we're trying to accomplish here. Acceleration. What's the unit for acceleration? Meters per second squared. Notice what I'm setting up right here. I have meters on the numerator, and then I have seconds, but I'm about to square it. So I'll end up having meters per second squared, which is the unit for acceleration, which is what I'm solving for, because it's what I need for F equals ma. But the question, the problem, gives information in centimeters. if I don't convert that into meters before I put it into my calculation, I'm going to end up with a unit of centimeters per second squared, which is not going to work. It's not going to work with the rest of my calculation, right? When I go to put in here, because remember, force is in terms of newtons. Okay, and remember, a newton is a kilogram times meters per second squared. Okay, and so if I plug in a unit for acceleration that has a centimeter per second squared into this equation, it's not going to work out well. It's not going to result in the appropriate unit. And so before I put this 85 centimeters into this equation, I need to turn it into meters, right? So that's going to help all of the units work out appropriately. All right. So let's do this. We're all ready to calculate there. And so I end up with, calculator tells me 6.8. And it looks like I should be using two significant figures. So yeah, 6.8 sounds good. And my units are, in fact, meters per second squared. Okay, cool. Now I'm going to take this acceleration, and I'm going to get through the traffic. I'm going to stick it into this equation here. All right, so I have F is equal to ma, and I know what mass is, 2.0 kilograms, and I just calculated acceleration. Let me get my calculator going here. 2.0 times 6.8, and I end up with 13.6. But looking at these two values that I'm using to actually carry out the calculation, let me move this up. I see that I should be using two significant figures. That's not two significant figures, so I need to round to this spot right here. So I'll really end up with 14. But what's the unit going to be? It's kilograms times meters per second squared. This is also known, aka a Newton. Right? It's a unit of force. So my final answer is 14 newtons. Now, take stock of what I did here. I needed to end up using Newton's second law, right? F equals ma. But I did not have a value for acceleration. But because of the information that was given to me by the problem, I was able to rearrange one of my kinematic equations to solve for acceleration. And once I solved for acceleration, it was pretty darn straightforward, like you've seen in the last couple of practice problems, to use Newton's second law to calculate force.